Hi there, today we're looking at rational expressions. So here I've got an example of a rational expression on the screen, and we're going to discuss what makes this a rational expression and what is its domain. So if you don't know the answers to these questions, continue watching and we'll find out. So first of all, what is a rational expression? So when we think about the word rational, you might think of something like logical, right? But actually, that's not what we're talking about. Instead, we want to think about the word ratio and what that means. We've seen this before when we talked about rational numbers. Rational numbers were numbers that could be expressed as a ratio or fraction of integers. So for example, the number 1/2, that's a ratio of two integers. So this is a rational number. Likewise, the number 5/4, this would also be a rational number. So when we talk about rational expressions, we're going to be talking about something that can be written as essentially a ratio of two polynomials. So it's some kind of algebraic expression that can be written as a ratio of two polynomials, right? Now, in general, fractional expressions are sort of a fraction or ratio of any type of algebraic expression. But for rational expressions, we are limiting ourselves to polynomials. Okay, so let's just try and review what a polynomial is. If you remember before, we were looking at polynomials, and they could be represented as the sum of a bunch of different terms. And each term would have some power, some x raised to some power. Now this power has to be a non-negative integer, right? So an integer greater than or equal to 0. And that's what we have all here, x to the 0, x to the 1, and these are all going to be positive integers over here. And then there's going to be a coefficient in front of each of these powers of x, and that coefficient can be pretty much anything. And a polynomial can have, one term, 10 terms, 2 terms, however many you want, each term being some sort of coefficient multiplied by x raised to some non-negative integer power. Okay, so that's what a polynomial is. And so we can try and look at a few examples of expressions. So for example, how about x squared over x cubed plus 1? Is this a rational expression? Well, the answer is yes, it is, right? Because on top here we have a polynomial, x squared, and on the bottom we have another polynomial, x cubed plus 1. That satisfies all of the rules about what a polynomial is. Okay, let's try another one. How about the number 1/2? Is this a rational expression? Well, technically, yes, it is. Okay, it's kind of an odd way to think about rational expressions, but it is in fact a rational expression. 1 is basically 1 times x to the 0, and 2 is 2 times x to the 0. These are both technically polynomials, so this would in fact be a rational expression. How about something like the square root of x over x plus 1? Is this a rational expression? Well, x to the 1/2, this is equal to x to the 1/2. 1/2 here is not an integer. It's not a non-negative integer, right? So this is actually not going to be a polynomial because x raised to the 1/2 is not a polynomial. The denominator is, but the numerator is not. How about trying another one? How about x over x squared plus 3x plus 10? Is this a rational expression? Well, is x a polynomial? Yes. Is the denominator a polynomial? Yes. Well, then there you go. This is a polynomial. And let's just try one more. Let's just try one more here. How about 2 raised to the x power over x squared minus 3? Is this a rational expression? Well, the denominator is a polynomial, but the numerator is not. Okay, so this would fail. 2 raised to some x power. This is some kind of exponential expression here, not a polynomial, so this would fail. Okay, so that's just a few examples. Now the question is, why bother thinking about rational expressions? Aren't polynomials good enough for us? Turns out they're not good enough. Why is that? Well, let's take a look here. If I add 2 polynomials together, I am guaranteed to get a third polynomial. For example, x squared plus 1, and let me add another polynomial, x. What do I get? Well, I'll just get x squared plus x plus 1, and this is in fact a polynomial, right? So if I understand polynomials, I understand whatever I get when I add them together, and that's really great. Now what about subtraction? Well, subtraction is going to be pretty much the same thing, right? Again, if I subtract two polynomials, just changing the sign here, I am guaranteed to get another polynomial out. What about multiplication? Okay, so let's try it. If I multiply x squared plus 1 times x, what do I get? Well, I'll get an x cubed plus x, and this is yet again another polynomial. We are guaranteed to get a polynomial when you multiply two polynomials together. Well, that leads us to division. Okay, so if we divide, the thing is we are not guaranteed to get a polynomial here. Let's take a look at this. If we do x squared plus 1 divided by x, what do we get? Well, we can sort of separate this and think about it as x squared over x plus 1 over x, and I could simplify this first term here into just x. The second one I can't really simplify, but I could write it as x to the power of negative 1. And now here, notice what we get. This is not a polynomial. A polynomial must have x raised to a non-negative integer. So the fact that this is negative 1 means this is no longer a polynomial. What is it? Well, it's a rational expression. That's what it is. It's not a polynomial. It's something new. It's something different. It's created by sort of combining or dividing polynomials. So you can think of polynomials as like a more fundamental object, and we use them to build this new kind of structure, a rational expression. So this is our chance to learn about how a new, more complicated structure can be created and what it behaves like and what we can do with it. And so that's why we get to rational expressions, because they can't be reduced to simply polynomials, which we already have some understanding about. All right, this brings us to the idea of domain and how rational expressions are a little bit different in their behavior than polynomials. And that's because if we look over here, we kind of see what a domain is. A domain is just this set of numbers that the variable is, we say, allowed to have inside of our algebraic expression. Now, what do I mean? Well, if we take a look at this first one, x squared over 10, this is perfectly fine, right? Now, I can put in any value I want for x, and I'll get a reasonable result. So for example, if I say that x is 1, right? If I put in a 1, I'll get a 1 squared over 10. Well, that's just a 1/10. That's fine. If I put x equals 2, I'll get a 2 squared over 10. Well, that's 4 over 10. That's just a number. That's 0.4. That's fine. If I put in negative 2, well, that's also fine. I could put in negative 2 squared over 10. Again, I'll get 4 over 10. Or I could put in a 0. 0 squared over 10, that's just 0. That's just a number. Everything is fine. So what we can say is that the domain for this algebraic expression, for this rational expression here, is, well, x can be any real number, right? X is allowed to be any real number, and we will get something reasonable as a result here. Now, what do I mean by that? Well, let's take a look at the next one here, 1 over x. I could do similar things. I could put in x equals 1. So if I do that, it's 1 over 1. That's just a number 1. That's fine. If I do 2, 1 over 2. That's valid output. If I do negative 2, I'll get 1 over negative 2. That's negative a half. That's fine. If I put in a 0, I'll get 1 over 0. And 1 over 0 is a problem because 1 over 0 is undefined. I cannot divide by 0. I cannot have 0 in the denominator. So now when I talk about my domain here, I have to be a little bit more careful because I cannot have x be 0. Okay, that is the key. So I'm going to say that my domain is any x that is in the set of real numbers, given that x is not equal to 0. All right, that's sort of the key here. I cannot have a 0 in the denominator. And so if I wanted to just keep that here as a rule, that's what I'm looking out for. The denominator cannot be 0 of my rational expression. So finally, let's take look at this third example here. X squared divided by x minus 5. What's the domain here? Well, the key is that the denominator cannot be equal to 0. That's when I get an undefined result. So I am trying to figure out when x minus 5 is not equal to 0. That's the danger zone, right? Well, if I add 5 to both sides, I'll get that x cannot equal 5. So when I write down my domain, I'll say that the domain is any x, which is an element of the set of real numbers, but I'm going to omit that. We're just kind of dealing with real numbers now. So any x such that x is not equal to 5. And that is going to be my domain for this rational expression x squared over x minus 5, because the domain can never be, the denominator can never be 0. That would give me an undefined number. That's not nice. All right, so let's try a few practice problems here. Why don't you pause the video, give these a try yourself, and then come back, we'll do them together. All right, so let's take a look at this first one, 3x cubed plus 4x minus 10. Well, here, there is no denominator. Denominator is just 1, so we don't have to worry about that. And x can be anything. X can be any number that is real. Any real number here works. So x is just an element of the set of real numbers, and that's good enough. Now for this second one, we do have a denominator of x plus 5. And we know there's a problem there if the denominator is equal to 0. So we want to make sure that x plus 5 does not equal 0. And for that to be true, we can just multiply or subtract 5 from both sides. So that's telling us that x cannot be equal to negative 5. So to write down the set here for all numbers that are in the domain here, we'll say that x, any x such that x is not equal to negative 5. Okay, so this is going to be our domain for this rational expression. And for the last rational expression, again, we have to make sure that our denominator does not equal 0. Okay, so how do we find when the denominator equals 0? Well, to do that, we're going to have to factor it. So we learned how to factor these types of expressions before, and we're looking for something that multiplies to give us positive 6, but sums to give us a negative 5. So that's sort of the idea here. So we're having factors of 6 that sum to give us negative 5. Okay, now, of course, we could have 1 and 6, but if I add these, I'll always get a positive number. And I want to get a negative number. So I have to look at the negative versions here. So negative 1 and negative 6, negative 2 and negative 3. Of course, negative 1 plus negative 6 is negative 7. Negative 2 plus negative 3 is negative 5. So yeah, this is going to be the one that we're looking for. This is going to be the factors that we're going to use here. So our factored form of the denominator will be x minus 2 times x minus 3. And the whole idea is that this cannot equal 0. So now I can just look at these two factors. And this first one is telling me that, well, x minus 2 cannot be 0. And this is telling me that x minus 3 cannot be 0. Why is that? Well, if I add plus 2 to both, or add 2 to both sides, I'll get x cannot equal 2. And here I'll get that x cannot equal 3. So let's think about that. If x was 2, 2 minus 2 is 0. 0 minus anything is 0. And so when x is 2, this entire quantity is 0. Same thing when x is 3. When x is 3, this is 0, and thus 0 times anything is 0, and so that's where the problem is. Okay, so these are the two values that if I plug in for x, I'll get 0 for the denominator. And so what this tells me then is that essentially the domain for my rational function is going to be all x such that x is not equal to 2 and x is not equal to 3. Okay, so there we go. That's going to be the domain for the last rational expression. Hopefully that helped out. And now you can understand what a rational expression is. It's a ratio of polynomials. And what the domain of a rational expression is. It's typically any real number except when the denominator is 0. All right, I'll see you next time when we continue to learn more about rational expressions.